So have you ever wondered how scientists talk about, say, the distance to another galaxy without writing a number that fills up an entire page, or how they can possibly describe the weight of a single atom? Well, in science, we're constantly dealing with numbers that are just ridiculously large or impossibly small. Today, we're going to crack the code they use to do it. It's a tool that turns total chaos into perfect clarity.
Here's our game plan. First, we'll look at the problem of numbers gone wild. Then, we'll reveal the secret code science uses to tame them. After that, you're going to master how to convert and calculate with this code. And finally, we'll see how it helps us make sense of scale and precision across the entire universe.
All right, so first up, why do we even need a whole special system for this? Well, the simple answer is that writing numbers out the long way is, well, it's a huge mess.
Just take a look at this beast. This is Avogadro's constant. It's a really important number in chemistry, but wow, is it huge. It's super awkward to write, it's a nightmare to read, and can you even imagine trying to punch that into your calculator without making a single mistake? You're just asking for trouble.
It just feels wrong, doesn't it? There has to be a smarter, more elegant way to handle a number like this. And hey, it's not just a big number problem. This is the mass of a single proton in grams. That's a decimal point, followed by 26 zeros, and then the numbers that matter. Again, it's just so clunky, and it's incredibly easy to accidentally add or lose a zero, which would throw the whole thing off completely.
Luckily, scientists figured out a brilliant solution for this ages ago, a kind of secret code that makes these wild numbers totally manageable. So, let's meet the hero of our story, scientific notation.
So what is it, really? The best way to think about it is like a zip file for numbers. It's a standard way to compress these long, unwieldy strings of digits into a format that's clean, compact, and just way easier to work with.
And here it is in action. On the left, you've got that numerical monster we saw before. And on the right, its sleek, elegant form, 6.022 times 10 to the 23rd power. It is the exact same number, but the difference is just night and day. One is pure chaos, the other is pure clarity. That's the power of this secret code.
And the real beauty of this system is how simple it is. It's only made of 3 parts. You've got the coefficient, that's the main number, and it's always going to be between 1 and 10. Then you have the base, which is always 10. And finally the exponent, which just tells you how many spots the decimal point had to move. That's the whole system right there. Okay, so now that you've seen what it can do, let's break down how you can actually use it. This is where you get the keys to the code.
For those huge numbers, the process is super straightforward. You start at the end of the number, and you just slide that decimal point to the left until there's only 1 digit in front of it. Then, you count how many places you moved, and that count, that's your positive exponent. Simple as that.
For the teeny tiny numbers, you guessed it, you do the exact opposite. You move the decimal point to the right to get your coefficient. And because you started with a number smaller than 1, your exponent is going to be negative. So remember, positive exponent for big numbers, negative for small ones.
Now, this isn't just about writing numbers neatly. The real magic, the real superpower, happens when you have to actually do math with them. Scientific notation turns ridiculously hard calculations into something that's, well, surprisingly simple.
So what if you need to multiply 2 massive numbers? Forget that long, painful process you learned in school. With scientific notation, you just multiply the coefficients, the front numbers, and then you just add the exponents. So, like 2 times 10 to the 3rd times 3 times 10 to the 4th is just 2 times 3, which is 6, and 3 plus 4, which is 7. The answer is just 6 times 10 to the 7th. Done.
Division is just as slick. You just divide the coefficients and then you subtract the exponents. So 8 times 10 to the 7 divided by 2 times 10 to the 3 becomes 8 divided by 2, that's 4. And 7 minus 3, that's also 4. The answer is 4 times 10 to the 4th. These simple rules just get rid of so much complexity and really cut down on silly mistakes.
Okay, let's build on that a little. Because beyond just writing and calculating, scientific notation unlocks our understanding of 2 really crucial ideas in science: scale and precision.
So first up is something called order of magnitude. Now that sounds kind of fancy, but it's really just a quick way of looking at the exponent, the power of 10, to get a rough ballpark idea of how big something is. It lets us compare things that are on completely different levels.
Check this out. The height of a person is roughly 10 to the power of 0 meters, which is just 1 meter. Mount Everest is around 10 to the 4th meters, and the Earth's diameter? That's about 10 to the 7th. Just by looking at the exponents, 0, 4, and 7, we can immediately grasp the incredible difference in scale without getting bogged down in the exact numbers.
The other key idea here is precision, and we talk about that using significant figures, or sig figs for short. These are basically the digits in a number that you can actually trust. They tell you how good your measurement tool was.
And what's so cool is that scientific notation makes seeing the precision super easy. All the digits you see in the coefficient are significant. So for Avogadro's constant, 6.022 times 10 to the 23rd, that coefficient, 6.022, tells us we have 4 significant figures. This means our measurement is reliable to that 4th digit. The notation automatically strips away all those extra placeholder zeros, leaving only the digits that really matter.
You know, when you boil it all down, what we're really talking about is a language. It's the language that science uses to describe reality at its absolute extremes, and getting a handle on it is just fundamental to understanding the world around us.
So just think about what we just did. In only a few minutes, you've cracked the code. You've gone from wrestling with these totally out-of-control numbers to being able to elegantly write them, calculate with them, and compare them. You've got a brand new lens to see the universe with both clarity and precision.
And that really just leaves us with one final thought. The tools are now in your hands. This code gives you the power to write down the distance to the farthest galaxy or the size of the tiniest particle. So the only question left is, what will you choose to measure?